In this video, we'll consider one example on design of digital filter. Define a second order digital low pass Butterworth filter with a cutoff frequency of 3.4 kHz at a sampling frequency of 8000 Hz. Use bilinear transformation. Also draw direct form 2 structure of this filter. So in this example, the cutoff frequency Fc is given, that is Fc is equal to 3.4 kilohertz, that is nothing but 3400 hertz. Along with that, a sampling frequency is given, that is Fs is equal to 8000 hertz. From this we can obtain T, which is equal to 1 upon Fs, that is nothing but 1 upon 8000 seconds. So to design a digital filter using bilinear transformation, the first step is we have to obtain digital frequency. Obtain digital frequency. The formula is omega c is equal to omega c into T radians. So here we can say omega c is digital frequency in radians, and this omega c is analog frequency in radians per second, and T is time period. So now I can calculate omega c is equal to, so this omega c can be represented as 2 pi fc, because here in problem fc is given, that is frequency is given, we are supposed to convert this into radians per second into T. Therefore I can write omega c is equal to 2 pi into fc value is 3400 into T value is 1 upon 8000. So simplifying this, we'll get 0.85 pi radians. Now the second step in bilinear transformation is we supposed to obtain pre-warped analog frequency, that is obtain pre-warped analog frequency. The formula is given by two by T tan omega c by 2. So therefore we can substitute the values 2 by T tan, here omega c is already we have calculated, that is 0.85 pi, 0.85 pi divided by 2. So simplifying, or I can write it as 2 by, so T value is given in the problem, that is 1 upon 8000. So now I can represent it as 2 into 8000 into tan 0.85 pi by 2. So simplifying this, we can get omega c is equal to 6.6645 into 10 power 4 radians per second. So in this example, the order of the filter is given, that is n is equal to 2. So now we are supposed to obtain the prototype transfer function or normalized transfer function for n equal to 2. Let that be our step 3. That is prototype transfer function, or it is also known as normalized transfer function. for n equal to 2 is given by, that is prototype transfer function hp of s is equal to 1 upon s square root 2s plus 1, or it can also be represented as 1 upon s square plus root 2 is nothing but 1.4142s plus 1. So now we know that to design the digital filter, first we supposed to design the analog filter. Then by using digital transformation method, we supposed to convert analog filter into digital filter. So with the help of prototype transfer function, now we'll design the low pass analog filter. Let that be our fourth step. Obtain analog low pass filter transfer function be obtained as h of s is equal to hp of s, replacing each s by omega c. So here h of s is transfer function of low pass filter, hp of s is prototype transfer function that we have solved in step number 3. So in that, in hp of s we supposed to replace each s by omega c, that is nothing but s divided by 6.6645 into 10 power 4. So therefore now I can write h of s is equal to, the value of hp of s is given by 1 upon s square plus 1.4142s plus 1. So in this, s should be replaced by s divided by 6.6645 into 10 power 4. So now I will try to simplify this. H of s is equal to 1 upon s square, that is s divided by 6.6645 into 10 power 4 square plus 1.4142 into s divided by 6.6645 into 10 power 4 plus 1. So further I can simplify this as h of s is equal to 1 upon, so here I will take this as LCM, that is 6.6645 into 10 power 4 square. So here I can get s square plus here one term will get cancelled, so I can get 1.4142 into 6.6645 into 10 power 4 s plus here the entire term will be multiplied, that is 6.6654 into 10 power 4 square. So further simplifying this, I can represent it as this will go into the numerator. So value of this will be that is 4.4416 into 10 power 9 divided by, here we have s square plus so multiplying this term with this term will get 9.4249 into 10 power 4 s plus the same numerator term, that is 4.4416 into 10 power 9. So this is the analog filter h of s. Now with the help of this h of s, we are supposed to obtain digital filter using bilinear transformation. H of z is equal to h of s, that is low pass filter transfer function, where s should be replaced by is 2 by t z minus 1 divided by z plus 1, which is equal to 16,000, that is 2 into t is 1 upon 8,000, that will become 16,000 z minus 1 divided by z plus 1. Now therefore this equation can be represented as, simplifying this, I can write h of z equal to, so it is on numerator we have 4.4416 into 10 power 9, denominator each s should be replaced by this entire term, it has 16,000 into z minus 1 divided by z plus 1 whole square, that is s square, plus 9.424 into 10 power 4 into 16,000 z minus 1 divided by z plus 1, plus we have another term, that is 4.4416 into 10 power 9. This is entire term is denominator. So for easy simplification, I will divide numerator and denominator by 16,000 square. That is, divide numerator and denominator by 16,000 square. Therefore, I can get h of z is equal to, on numerator by dividing 16,000 square, will get 17.35 divided by, here this 16,000 square and this will be get cancelled, will remains only this term, that is z minus 1 divided by z plus 1 square, plus, so dividing 9.424 10 power 4 divided by 16,000, it gives 5.8906 z minus 1 divided by z plus 1, plus dividing this by 16,000 is nothing but 17.35. We'll try to simplify this further. We'll divide numerator and denominator by z plus 1 square. That is, divide numerator and denominator by z plus 1 square, so that I can represent it as h of z is equal to 17.35 z plus 1 square divided by, here this will get cancelled, remaining term is z minus 1 square plus 5.8906, we have z minus 1 and one more term will be z plus 1, as one z plus 1 will get cancelled, plus 17.35 z plus 1 square. So simplifying this further, 17.35, simplifying this, z square plus 2z plus 1, and on denominator side we have z square minus 2z plus 1 plus 5.8906 z square minus 1, as here it is a minus b, a plus b form, a square minus b square. Here we have 17.35 z square plus 2z plus 1. Simplify this as h of z is equal to, and multiply this 17.35 with all these terms, I'll get 17.35 z square plus 34.7 z plus 17.35 on denominator. After simplifying this, here we can see the coefficient of z square, that is here we have 1 plus 5.8906 plus 17.35, which leads to 24.2406 z square plus, now we'll see the coefficient of z. Here we have minus 2 and here we have 17.35 into 2, that will get 32.7 z plus the constant. Here we have 17.35 minus 5.8906, it leads to 12.4594. So now we'll try to represent this in standard form. To represent h of z in a standard form, divide numerator and denominator by 06 z square, 24.2406 z square. Therefore I can write h of z is equal to, here 17.35 divided by this, it gives 0.7157 plus 34.7 z divided by this term, it gives 1.4314 z inverse plus, here we can get 17.35 divided by this term gives 0.7151 z power minus 2 divided by, here we have 1 plus this term divided by this, it gives 1.3490 z inverse plus this term divided by this gives 0.5140 z power minus 2. So this is the transfer function of digital filter, that is h of z. So now we'll try to obtain direct form 2 structure from this h of z. So we know that in IR filter the numerator is with respect to zeros and denominator is with respect to poles. Therefore now I can represent the transfer function h of z as h of z is equal to y of z by x of z. In turn I will represent it as, that is, I'll take one intermediate output, say w of z by x of z into x of z into, we have y of z by w of z. It is same as this equation where if you cancel w of z and w of z, we will get the same term. Therefore now I can represent it as, now I'll consider this term as h1 of z and this term as h2 of z. So therefore h1 of z is equal to w of z divided by x of z, which is equal to 1 upon x of z is with respect to poles, that is 1 upon 1 plus, these are the poles, denominator represent poles, 1.35 z inverse, I will round it off to 5 plus 0.51 z power minus 2 So I'll perform cross multiplication here, that is I can represent it as W of Z plus 1.35 Z inverse W of Z plus 0.51 Z power minus 2 W of Z is equal to X of Z. Therefore, I can represent it as W of Z is equal to X of Z minus 1.35 Z inverse W of Z minus 0.51 Z power minus 2 W of Z. Now taking inverse Z transform, you can represent it as W of n is equal to X of n minus 1.35 W of n minus 1 minus 0.51 W of n minus 2. So we'll call it as equation number 1. H2 of Z is equal to Y of Z divided by W of Z is equal to, this is with respect to numerator, that is nothing but zeros, that is 0.7157. So now cross multiplying, I can write Y of Z is equal to W of Z into 0.715 plus W of Z into Z inverse into 1.43 plus W of Z into Z power minus 2 into 0.71. Now taking inverse Z transform, I can write Y of n is equal to (0.71) W of n plus 1.43 W of n minus 1 plus 0.71 W of n minus 2. So we'll call here this equation as 2. Now using 1 and 2, we can directly draw the structure as, say we need one adder here. So let this point be, so let this be X of n, this be Y of n, and this be intermediate result, that is W of n. So now from equation 1 we have W of n is equal to X of n. Here we get X of n minus 1.35 W of n minus 1. To get W of n minus 1, we are supposed to pass W of n through one delay element. So output of this is W of n minus 1. So it should be multiplied by minus 1.35. So let this be multiplied by minus 1.35. So it should be added with another delay element, as there is W of n minus 2. Pass through this another delay element. The output of this is W of n minus 2. It should be multiplied with minus 0.51. That is, this is minus 0.51. Now with respect to equation 2, it is output expression Y of n, which is equal to 0.71 Wn. So here Wn is available, we should multiply it with 0.71. So it will become 0.71 Wn. Here we have 1.43 W of n minus 1. So here we have W of n minus 1 signal is available. Pass this and multiply this with 1.43. Similarly, we have W of n minus 2. Here W of n minus 2 is available. It should be multiplied with 0.71. That is 0.71. That is 0.71 it should be connected here. Similarly, this should be connected here. So this is direct form 2 structure for the designed digital filter H of Z. Thank you for watching.